Hello everyone, and thanks for watching Edupedia World Videos. In this video, we'll apply some previously learned concepts to a very special kind of charge distribution called electric dipoles. The concepts which we'll use are the concepts of electric forces, which gives rise to the concepts of electric fields, which help us with the concepts of potentials. So we've done all this for a single point charge Q. Now we'll do this for the next best step, and that is a case which arises quite frequently in real life solutions, and that is an electric dipole. An electric dipole consists of two equal and opposite charges. Let's say one is a positive charge plus Q and the other is a negative charge minus Q, separated by a small distance d. Now when we say small distance, it has to be relative to something. So let's say it's relative to a faraway point. This distance is r. That means if we want to calculate the electric field or potential at this point due to this charge configuration, then in the cases where r is much greater than d, we will use what is called the electric dipole approximation, and those formulas will be standard, which we'll remember always, and those formulas will be for this electric dipole. So this particular quantity is called a dipole. The formulas which we'll remember for the electric dipole, they will not be valid for this point because this point is quite close to the dipole. They will only be valid for the points far away from the dipole, right? And that is called the dipole approximation. So let's get down to the basic mathematics of it. We have one charge, positive charge Q, and we have a negative charge minus Q, and let's say they are separated by a distance d, and we want to calculate the electric field and the potential due to this particular system at a point P, which is at a distance r away from the center of the dipole, and this angle is theta. So if we take this distance and this distance, so let's call this r positive and this r negative. So the net potential at P will be the potential due to the first one plus the potential due to the second one. This comes from the superposition principle. If the forces are the superposition of individual forces, fields are the superposition of individual fields, and because of that, potentials are the superposition of individual potentials. So the first one will give us kq by r plus, the second one will give us k times minus q by r minus, which can be written as kq times 1 by r plus minus 1 by r minus. Now the whole game is to write r plus and r minus in terms of r and d, right? So if we extend this a little bit further, we can see that since r is much greater than d, when we construct a perpendicular, we can assume that r plus is the same as this distance going from P to this point O, because they can be assumed to be two radii of a circle. They can be assumed to be an isosceles triangle. Now if this whole thing is d, then this is d by 2 and this is theta, so this is d by 2 cos theta. Similarly, we can draw a perpendicular here, and this will also be d by 2 cos theta. So we can see that r plus is approximately equal to r, that is A, B, this is O, and this is C. So r plus, which is PA, can be approximately seen to be equal to PC plus PO, that is PO, PA equal to PO, right? PC plus PO will be r plus d by 2 cos theta. Similarly, r minus can be seen to be, if this distance is capital Q, then r minus can be equal to PQ, and PQ is PC minus CQ. So this will be r minus d by 2 cos theta. It's a little bit of mathematics and geometry. I hope you try this at home yourself as well. So after writing these two, it becomes easy enough. What we get is V is equal to KQ 1 by r plus d by 2 cos theta minus 1 by r minus d by 2 cos theta. You take the LCM and you simplify it, and eventually the answer you will get is k into q into d cos theta because r minus d by 2 cos theta and r plus d by 2 cos theta when subtracted will give me twice of d by 2 cos theta, so d cos theta divided by r square minus d square by 4 cos square theta. Right. Now since d is much smaller than r, we can neglect it in front of this, and the final result we get is v is equal to k qd cos theta by r square. Right. So let's look at this again. We have a positive charge and a negative charge. Distance between them is d, magnitude is q. A distance r away from it at an angle theta, the potential is found to be k qd cos theta by r square. Now qd is a very special quantity that is denoted as p, and that is called the dipole moment. Every dipole has its own dipole moment, which is q multiplied by d. Now here students sometimes have confusion. They assume q is the charge on the dipole. No, the charge on the dipole is 0, right? Because you have a positive charge and you have an equally negative charge. So q is not the total charge on the dipole. It is either the positive charge or the negative charge magnitude. One of the two charges multiplied by the distance between them. From this we get the result that v is equal to k p cos theta by r square. Right. So this is the most important result for dipoles, and it tells us the position in terms of two coordinates r and theta. Right. Now from this you can actually calculate the electric field in terms of r and theta as well. ER will be minus del V by del R, and that can be, if we differentiate with respect to r, minus 2 will be minus 3, so that will give me minus 2 kp cos theta by r cube. That is the electric field in the radial direction, but the electric field might also have a tangential component. ET will be minus del V by a small change in this displacement. Right, dr was a small change in r, a small change in this displacement. If this is theta, d theta will be r times d theta. So it will be r times d theta or r times del theta. Cos theta's derivative will be sin theta, so this will give me minus kp sin theta by r cube. So for any dipole, given any r and theta, we've been able to calculate the potential, that is kp cos theta by r square, and using this potential we've been able to calculate the electric fields. The radial one is minus 2 kp cos theta by r cube, and the tangential one is minus kp sin theta by r cube. Now a couple of other important things. One, the dipole moment is generally taken to be a vector whose magnitude is qd and whose direction is from negative to positive. So if this is the dipole, then this will be the direction of the dipole moment, from negative to positive. One thing I would suggest to you is try to get ER and ET the way we got P. For potential, the way we got V. We added the potential at these 2 points, and that gave us the potential at this point due to the combined system, and from that we got E, but we could actually write the electric field due to the two charges individually and add them up and simplify it, and you should get finally a vector which has two components, ER and ET. Those components will be this particular thing. It will be slightly more complicated mathematically, but it will give you a better understanding, so I suggest you do it. Now a couple of other definitions. Theta is equal to 0 is called the ends-on position. That means theta will be 0 in this direction. So if in the question is given that a particle is placed at the ends-on position of a dipole and 10 meters away from the negative charge, then you'll know that it's on this axis and in this direction 10 meters away. Right. Theta is equal to 90 degrees is also a special point, that is called the broadside on position. So if the question says that a particle is kept on the broadside on position of a dipole 10 meters away, that means it is kept 10 meters away. here, right? So the moment we've calculated the potential and the field, there are a couple of other things which you can see for dipoles as well. One is the torque on a dipole when it is kept in a uniform electric field. So let's say positive charge, negative charge, distance is d, let's say this angle is theta, and let's say we have an electric field E, right? So this particular particle will experience a force in this direction, QE, and this negative particle will experience a force, the positive particle will experience a force towards the right, QE, the negative particle will experience a force towards the left, QE. And these two forces will create a torque on the dipole. The value of the torque will be 2 times QE into this distance. This distance is d by 2 sine theta, which is the same as QD E sine theta. And because it's sine theta which comes in cross product, we can actually write this vectorially as torque is equal to P cross E. This is the torque experienced by a dipole of dipole moment P in an electric field E. Now E is in this direction and dipole moment is in this direction. And you can see P cross E comes towards you, towards the observer if you're looking from the screen. And that is the direction towards the observer in which this dipole has a tendency to rotate. So if a dipole is placed in a uniform electric field, it has a torque, it experiences a torque which is the same as P cross E. If it is in this direction, P is parallel to E, then it will not experience any torque, and when it is perpendicular, it will experience the maximum torque. Finally, one last concept, the potential energy of a dipole in a uniform electric field. So let's say the dipole we had previously, this is the direction of electric field, this is theta, positive, negative. Let's say the dipole changes its orientation slightly by an amount d theta. In that case, the small amount of work done by the electric forces will be equal to tau d theta, and that will be equal to minus Pe sine theta d theta. Now du, which is the change in electromagnetic potential energy, will be Pe sine theta d theta. You integrate it to get the total potential energy, and what we'll do is we'll take the potential energy to be 0 when theta is 90 degrees. That means when it is perpendicular to the electric field, that's when the potential energy is 0, right? So here we'll get u and here we'll get theta. So what we get is u is equal to the integral of sine theta will be minus cos theta, so it will give me minus Pe cos theta, which can be written as minus P dot E. So we got the torque as P cross E for a dipole placed in a uniform electric field, and the potential energy is minus P dot E. Again, the moment you talk of potential energy, the reference point needs to be given. So this is the formula assuming u is equal to 0 when theta is equal to 90 degree. That means theta is equal to 90 degrees is the maximum energy. If we take that to be 0, every energy will be smaller than that. And we see that it is minimum when P is parallel to E. So electric fields have a tendency to rotate the dipole parallel to them. Right. The reason this is useful is because actually the dipoles are not always a positive and a negative charge. The generalized definition of a dipole is actually if V as a function of r and theta is equal to kp cos theta by r square. If for any particular configuration of charges, the potential at a distance r at an angle theta from a reference is given by a formula like this, then P is called the dipole moment of that configuration. So that's the general formula, but that specifically also applies when we have a positive charge and a negative charge. The advantage is, for example, we have a if we have a water molecule which has 2 hydrogen and an oxygen here, right? So since the oxygen is more electronegative, it creates a net dipole moment. It creates a negative charge here and a positive charge here, which creates a net dipole moment. So all you need to do is somehow measure the dipole moment of a water molecule. Now, it's not strictly a one positive and one negative charge, but if we measure the potential at a distance r and theta away and we map that according to this, we can see that it forms this pattern, and P could be the dipole moment. So once we measure the dipole moment, every result which we viewed till now can be used directly for water molecules. That is not strictly a dipole. So this is the advantage of using the formulation of dipole moment. Thank you.